I felt like I was doing really well when he was nodding along, like he was understanding what I was saying, so. When we look at the cross-section of energy use right now in the world, there's a relatively small component of it that is commercial aviation. So it's not the biggest piece that we need to tackle, but it's something that we definitely need to think about. When it comes to making aviation more sustainable, I'd say there's kind of 4 buckets. So one of them is to look at hybrid electric propulsion. Another would be to use sustainable aviation fuels. Another would be hydrogen fuel. And another would probably be all-electric propulsion. So if we look at those 4 solutions though, the first 3 that I listed, all are going to require a highly efficient gas turbine at the core. As gas turbine engines have evolved over the last several decades, what we've seen is that the temperature at the highest point of the engine going into the turbine has continued to increase. The reason for this is because from a thermodynamics fundamental engineering perspective, the easiest way to increase the efficiency of an engine or a cycle is to increase the hottest temperature of that cycle. The problem with that though is that these temperatures are like hotter than lava, several thousands of degrees Fahrenheit. They melt rocks, they melt metal. And so in order to make sure that these pieces, these critical turbine components that are rotating in the engine aren't going to melt and disappear, they have to have features inside them that allow cooling air to pass through them. So this means that turbine blades are effectively hollow on the inside. As those temperatures continued to get higher and higher and higher, we started adding external film cooling holes. So then that would create these small, tiny holes that for an aircraft engine might be on the order of 30 thousandths of an inch or even smaller. They started as just drilled round holes. Now they've become these highly engineered features that have complex shapes to them. And so then what we're left with is this turbine blade that has internal air going through it, has this safety blanket of cold air that's flowing around it through these cooling holes, and that's what helps to make sure that the blade is going to stay safe and survive for its life. And that's a lot of the research that we contribute to here at Penn State in the STAR Lab, optimizing and figuring out how to create new holes that are more efficient in their operation. So we've worked collaboratively with Pratt & Whitney, the Department of Energy, the United States Air Force, and several other people to create some really unique measurement capabilities. Non-contact thermal imaging approach uses infrared technology. Some people use infrared technology to take pictures of their walls in their house to see how well it's insulated, or it has a lot of applications in the military to see where heat is located from different kinds of sources. We use it by actually taking thermal images inside our operating research turbine here at Penn State in the STAR Lab. Increasing the temperature of the blade by maybe 50 degrees or so, or even less, can actually cause the life of that part to decrease by a factor of 2. With that technology then, we can get a full spatial map of temperatures across the entire blade, so we can understand what's happening from the temperatures due to the internal cooling that's passing through it, and also that external cooling that's present from the film cooling holes. And so then we can better nail down those temperatures so that we can make sure we're not going to miss that 50 degrees or so, because that 50 degrees can be a huge, huge miss in terms of how long the parts are going to last. And ultimately, we want these parts to last so that the engines continue to fly, right? Everybody wants their engines to fly. The passengers want them to fly. The owners, the airlines, they want the engines to stay on the plane. And that's all the stuff that we're working to fix.